So, welcome to our lecture series on advanced linear algebra. In my last class, we have discussed about the direct sum decompositions of subspaces of a vector space V, where subspaces are invariant under T. We have seen under what condition the subspaces will be invariant, and then we have applied this concept to a diagonalizable operator. So, let me summarize that what we have done last time and also answer the questions what I raised in last times in the form of this theorem, please. So, what is this? Let T be a linear operator on a finite dimensional vector space capital V over the field say capital F. So, let us summarize the result what we did in our last lectures and also answer the questions which I raised in the end of my lecture. So, I am summarizing in terms of this theorem please. It is like this, say T be a linear operator on a finite dimensional vector space V over the field capital F. If T is diagonalizable and if C1, C2, Ck are the distinct eigenvalues or characteristic values of T, then there exist k linear operators E1, E2, Ek on V satisfying first condition T equal to C1 E1 plus C2 E2 plus Ck Ek, and the identity operator is basically sum of E1 E2 Ek. Third, Ei into Ej equal to 0, and fourth Ei basically projection operator for each I. And the last one, the range of Ei is Wi. If I consider T is diagonalizable, so certainly the space V will be direct sums of its characteristic spaces, and as a consequence of it you will have, one can introduce the projection operator E1, E2, Ek satisfying all four conditions please, which we have already seen in our last lectures. Now, the problem is converse. I mean to say, if there exist k distinct scalars C1, C2, Ck and k linear operators, non-zero linear operators E1, E2, Ek satisfying condition 1, 2, 3, that the operator T as a sum of C1 E1 plus C2 E2 plus Ck Ek and identity operator as a sum of this k linear operator, non-zero linear operator E1 to Ek, and the linear operator Ei such that Ei into Ej equal to 0 when I not equal to 0, then T is diagonalizable, and C1, C2, Ck are the basically distinct eigenvalues of this operator T, and conditions 4 and 5, that is each Ei here will be projection operators and the range of Ei will be Wi. So, the done. So, now I will to prove basically the converse part please. We want to so we want to prove converse one. So, what we have to prove? So, we have to prove show first each Ei is a projection, First we have to prove each Ei is projection. Second, each Ci is eigenvalue of T, and these are also only eigenvalues of T. And third one, the range space of each Ei is null space of T minus C I I. If I prove this thing, this 3, then certainly T will be diagonalizables. So, that part will be over, please. Okay. We have from given condition I equal to E1 plus E2 plus Ek implies if I multiplied Ej from the left side to the both these equations, we have Eji equal to Ej E1 plus Ej E2 plus Ej Ek. Okay, so this is equal to Ej into Ej, that is Ej square, since Ei Ej equal to 0 for I not equal to j, it is given to us. So, this implies Ej equal to Ej square implies Ej is a projection. Ej is a projection of the space V, please. Okay, so it is a projection operator, please. For each j, that j equal to 1 to k, please. Now, we want to show that Ci, that constant C1 to Ck are basically eigenvalues of T. We have T equal to, it is given to us C1 E1 plus C2 E2 plus Ck Ek. So, it is given to us like this. So, this implies that T Ej equal to, I can write down Ci Ei Ej I equal to 1 to k. So, T Ei Ej equal to this quantity, this is equal to Ci and Ej. So, this implies that T minus Cj and identity operator operating on basically and composition of the operator T minus Cj I and Ej equal to 0. I will get 0 operator, please. Given each Ej is non-zero linear operator. So, this implies there exists alpha belongs to V such that Ej alpha not equal to 0. So, this implies T minus Cj I, this implies T minus Cj I Ej alpha equal to 0, where Ej alpha not equal to 0. So, this implies Cj is an eigenvalue of T, because T of Ej alpha equal to Cj into Ej alpha, where Ej alpha not equal to 0. So, Cj is an eigenvalue of T, please. And this is true for j equal to 1 to k, for j equal to 1 to k, because I have multiplied Ej, you can do for E1, E2, Ek, and we have that each Ci. So, each Ci is eigenvalue of T, please. Now, we also have from T minus Cj I into Ej equal to 0, this equal to 0 implies for any alpha belongs to range of Ej, that is alpha equal to Ej alpha t minus Cj I Ej alpha equal to 0. So, this implies range space of Ej is a subset, the subset of null space of T minus Cj I, this operator. So, you see that the range space of the each Ej operator, which I have proved is the projection operator, is basically a subset or subspace of the null space of T minus Cj I. I want to show that the range space of Ej is exactly equal to null space of T minus Cj I. But before proving that once, let me first prove that C1, C2, Ck are the only eigenvalues of the operator T. Claim C1, C2, Ck are only eigenvalues of T. Suppose not, suppose not. Let C not equal to Ci, I equal to 1 to k belongs to F such that T of alpha equal to C alpha for some 0 not equal to alpha belongs to V. So, this implies T minus Ci operating on alpha equal to 0. According to given condition, we have T equal to C1 E1 plus C2 E2 plus Ck Ek and I equal to E1 plus Ek. So, this implies that T minus Ci will be equal to sigma Ci minus C into Ei, I equal to 1 to k. So, just if I multiply C both the sides, then I am getting C. Okay. So, if I multiply C to both the sides of this expression I equal to E1 plus E2 Ek, I will have T and subtract that T and minus Ci if I consider, then I am having basically sigma I equal to 1 to k C1 minus C E1 plus C2 minus C E2 plus and dot dot up to Ck minus C into Ek please. So, I have like this thing please. Now, we have according to our hypothesis T minus Ci operating on alpha equal to 0. This implies that sigma Ci minus C Ei operating on alpha equal to 0, I equal to 1 to k. Sigma Ci minus C into Ei, I equal to 1 to k alpha equal to 0 implies if I multiply Ej from the both the sides, then I am having basically sigma and Ci minus C is a constant. So, I can take it out Ci minus C into Ej Ei alpha I equal to 1 to k equal to 0 implies that Cj minus C into Ej alpha equal to 0 and this is true for j equal to 1 to k, because I have multiplied Ej and I am getting this one. If I multiplied for j equal to 1 to 3, then I will also have this type of relation, that Cj minus C into Ej when this operator operating on alpha equal to 0. Okay. Alpha not equal to 0. This implies that, according to the structure given condition, alpha is equal to E1 alpha plus E2 alpha plus Ek alpha. So, certainly for some j not equal to 0. So, Ej alpha not equal to 0, this implies that then Cj minus C equal to 0, because product of two non-zero quantity number cannot be 0 over the field capital F. So, Cj minus C equal to 0. So, this implies Cj equal to C. So, this implies C1, C2, Ck are the only eigenvalues of the operator T. Okay, so, if I somehow can show that range space of each Ej is exactly null space of T minus Cji, then I can say that the operator T is diagonalizable. So, now we want to show the null space of T minus Cji is also a subset, of range space of Ej. So, you want to show this one, please. So, let alpha belongs to null space of T minus Cji, this operator. So, this implies that T minus Cji alpha equal to 0, but according to given condition, T minus Cji alpha is equal to 0, this is equal to, I can write down, this is equal to sigma Ci minus Cj and Ei alpha, I equal to 1 to k, okay, this is equal to 0, please. So, this implies sigma I equal to 1 to k Ci minus Cj into Ei alpha equal to 0, because T is equal to what? T equal to C1 E1 plus C2 E2 plus Ck Ek and I equal to E1 plus E2 plus Ek. So, Cj times I will be Cj E1 plus Cj E2 plus Cj Ek. So, when I consider T minus Cji, this is equal to sigma Ci minus Cj into Ei, and then operating on alpha I will have like this thing, please. So, this implies that if I multiplied E small s from the both these sides, I will have sigma Ci minus Cj into E small s and the Ei alpha, your I equal to 1 to k. So, this will be equal to, again I can say Cs minus Cj, into E square alpha equal to 0, because Es into Ei equal to 0 when I not equal to S. So, that this implies that I will have this type of relation please. So, this implies Cs minus Cj into Es alpha equal to 0. Now, this is again true for all S equal to 1 to k except S equal to j, because I am getting when S equal to j, Cj minus Cj equal to 0. So, it is not coming to the picture please. Now, since Cs minus Cj is not equal to 0 for S not equal to j, so this implies Es alpha equal to 0 for all S except S equal to j. So, we know alpha is equal to E1 alpha plus E2 alpha plus Ek alpha. So, since Ei alpha equal to 0 for I not equal to j, so this implies alpha is equal to Ej alpha only. So, this implies alpha belongs to range of Ej. So, this implies the null space of T minus Cji is also a subset of range of Ej. So, already we have seen the range of Ej is a subspace of null space of T minus Cji, and now I am showing that null space of T minus Cji is subspace of range of Ej. So, from these two results I can say that null space of T minus Cji is exactly equal to range space of Ej. So, what we have seen it here, when we have a linear operator T defined on the vector space V, and when there are k distinct scalars C1, C2, Ck and k distinct non-zero linear operator E1, E2, Ek, and the operators E1, E2, Ek satisfied the condition that the operator T can be written as sum of C1, E1 plus C2, E2 plus Ck, Ek, and identity operator can be written as E1 plus E2 plus Ek, and the operator Ei having characteristic that Ei into Ej equal to 0, 0 operator when I not equal to 0, then we have seen that each Ei here is basically projection operator and projection of the space V, and C1, C2, Ck are distinct eigenvalues, and these are also only eigenvalues of the operator T, and range space of each linear operator Ei is basically null space of T minus Cii. So, the operator T is then direct sums of subspaces W1, W2, Wk, and so it is a diagonalizable operator please. So, T is a diagonalizable operator on the space V please. So, this results basically will encourage us to think about when the operator T is not diagonalizable. In that case, what will be the structure of the projection operator when the space is decomposed by some direct sum of subspaces of corresponding vector space. So, this will certainly give a clue which we will discuss in the next class please.